Hey dear all, welcome to traffic characteristics class. So even though our main focus of the highway engineering is to design the highway, including the geometric design and pavement design. But before we go to the details of design, we have to understand the traffic characteristics. In last class, we already understand the road user characteristics. So now we need to get familiar with the traffic characteristics, which include the traffic flow. And usually for the traffic flow, they have different characteristics, include the speeds and traffic volume, all right, and also the density. So our learning objectives will cover all those traffic flow characteristics, including the different types of speeds, and describe how to calculate the time mean and the space mean speed, and describe how to calculate the running and overall speed, and also describe the difference between traffic volume and rate of flow volume. In addition to that, we will also describe how to calculate the peak hours factor. After we are done with this class, you are expected to memorize the relationship between speed, volume, and density. And finally, we'll describe how to calculate the time headway and the space headway. So now let's go to the first traffic flow characteristics, which is called travel speed. So based on what we have learned in probably high school, we know the traffic speed is defined as the total distance traversed divided by the travel time. So for example, in this case, we have a roadway, and that's the distance in between. Okay, and with this distance, maybe it take about time t for you to finish traversing this roadway sections. So if your t is second and then your roadway length is meters, then your speed can be expressed by meter per second. All right, again, if your roadway section is expressed in feet, then your speed will be feet per second. And then if your length is miles and your time is hours, you have miles per hour, and so on. That's the travel speed. Relatively easy, but that's just the general definition. In our transportation engineering field, we have three types of travel speed. Basically, we have spot speed, running speed, and overall speed. Let's pause a little bit right here and see what's the difference between the three types of speed. If you look at clearly, you can see the spot speed actually represents what? The relative short distance. And the running speed and overall speed both cover relatively long distance. So that's their major difference. So even though we have three types, but if you want to classify them in two types, I would put spot speed as one type and running speed and overall speed as another type. So the difference of running speed and overall speed is their travel time. The running speed, we only include the travel time covering the motion time only. The stop delay time will be excluded. And so for the overall speed, we include all the travel times, including the motion time and the stop delay time as well. So let's see examples. Let's assume we have distance which represented by d, and that's your starting point A, and that's your end point B. Okay, the travel time, there is also a signal in the middle. Okay, signal in the middle. You have to memorize, okay, the top signal is what? Is the is what? Is green or red? It's up to you to check by yourself. All right. Now, the total travel time, let's assume the first part of a motion time between A and C is t1, and then between C, we stop at the signal with time t2, and then between C and B we have travel time of t3. So in this case, what is the running speed? The VR will be equals to what? VR just includes the travel time, the motion time only, will be the d divided by t1 plus t2 or t3, because the stop and delay time not included. And the overall speed actually includes the distance, which is d, divided by the total travel time, including the motion time, and also includes the stop and delay time at the signal t2, and then includes t3 as well. So that's the difference between the running speed and the overall speed. And a small speed, it covers relatively short distance, so usually we can measure the time by using the laser, the radar gun, and camera, or manually just by stopwatch. Okay, so these slides demonstrate the spot speed measuring device, the radar, the handheld laser gun, the dash-mounted radar, and also the cameras and stopwatch. The stopwatch manages to to measure the travel time between the relatively short distance, and then use the total distance divided by the running time right here. So for the spot speed, we are mainly concerned about their average spot speed, because for traffic flow we want to look at the whole traffic flow as a group. We don't care about the individual spot speed that much. Instead, we are more interested about the average spot speed. Usually we have two types of average spot speed, the time mean and the space mean. For the time mean, actually is you calculate the individual speed first, individual speed, and then calculate their average speed. All right, this is a typical arithmetic mean value we usually use. And the space mean is a little bit different. Space mean, you have to calculate their total distance divided by the total time. So the space mean actually focus on the entire traffic flow as the whole group. So they don't focus on the individual speed. They focus on the total distance traversed divided by the total time used. So basically in the transportation engineering field, if we say the average speed, if we didn't tell you which specific mean speed, by default we use the space mean speed, because the space mean is more closely related with the average speed we are using for dedicated to the whole volume. Usually the time mean speed is greater than the space mean speed. Let's see an example. If in the class folder, if you open the additional notes for speed, volume, and density, okay, you will be able to find this drawing right here. For this drawing, let's assume we have 100 feet distance, all right, relatively short, because we are talking about the spot speed. And assume we have 4 vehicles, vehicle 1, 2, 3, 4. It takes 3 seconds for the first vehicle to traverse this distance, and 4 seconds for the second vehicle, 5 seconds and 4 seconds for the third and fourth vehicles to traverse this distance. And based on the definition of time mean, we calculate the individual spot speed first. So in other words, the first vehicle that their individual speed is 100 divided by 3 seconds, and the second is 100 divided by 4, 100 divided by 5, and 100 divided by 4. And then we have 4 vehicles, so we divide by 4. That's their total time mean speed. And for the space mean, we use the total distance divided by the total time used. Total distance, we have 4 vehicles, the total distance is 400, and the total time is 3 plus 4 plus 5 plus 4. So the space mean speed is 25. So based on our previous discussion, you can tell, okay, this example clearly demonstrates the time mean is slightly larger than the space mean right here. Alright, so up to now we are done with the 3 types of speeds: the overall speed, the running speed, and the spot speed. And spot speed, we have 2 types of average spot speed: time mean and space mean. Now let's go to the traffic volume. Traffic volume, it's very similar to the drainage volume that you learned from the drainage class. Basically, it represents the number of vehicles that pass a roadway points per unit of time. Based on your unit time, it could be per day, could be per hour, could be per minute, okay? So the units usually is vehicle per day, vehicle per hour, or vehicles per minute. So similar to a speed, for the volume, we also have different types of volume measuring devices. The first, we have the video detectors. Okay, so lots of time you see some cameras mounted on the street lighting or the signal lights standard. Their main purpose is not to capture your license plate and to check whether you are speeding or not. Their main purpose is just to count how many vehicles pass these roadway sections. And in front of the signal lights, sometimes you see there are some loops on the pavement. Their main purpose is also to count how many vehicles crossing the intersections, so they can allocate the appropriate time, the green time, for different directions. And sometimes you have seen these tube detectors at some roadway sections. But compared with the loop detectors, the tube detectors usually are used on relatively small roadways with a smaller number of vehicles passing. Because this is tube, if there is lots of vehicles passing with relatively high speed like the freeway, this tube can be damaged very quickly. So these tube detectors are just simply used in those lowly frequently used roadways. And sometimes you find some people standing by the intersections and with a device on their hand. Okay, so this one is called handheld collectors. So clearly you can see they have different directions, and for each directions the man can just count the different directions when one vehicles pass for each directions. So this way they can store the information. Alright, so similar to speed, for travel volume, we have 4 major travel volume as well. The first one is called AADT. It's annual average daily traffic. Annual average daily traffic, that means the time period will be over 1 year. And for example, you count the traffic volume for 2 years in a row, and then you calculate the average number of vehicles per day. Okay, that's called AADT. And ADT is the average daily traffic. The unit is also vehicles per day, the same like ADT, but The difference is the time period is less than 1 year. For example, you go to fields and then you collect the 2 months or 3 months data, and then you calculate the average daily vehicles. All right. So which one is more accurate? 3 months time period versus 1 year time period, and they calculate their average number of vehicles per day. Which one is more accurate? Of course, the AADT will be more accurate. Why? Because some city, they have huge seasonal fluctuation in terms of the traffic volume. For example, in the winter time period, the traffic volume is relatively low, and for summer, the traffic volume is relatively high. So if your 3 time periods just only cover the summertime period, then your ADT will be relatively high. And if you only cover the winter time period, then your ADT will be relatively low. Okay, so if you want to get a more accurate, I highly recommend you to use the AADT rather than ADT. ADT is not that accurate, especially for those cities where the traffic volume is seasonally fluctuated. So both ADT and ADT, their unit is vehicle per day, number of vehicles per day. And for the design of roadways, usually we focus on the hourly volume. We don't care about the total number of vehicles per day. We actually are more interested for the vehicles per hour. Why? Because for the number of lanes, usually we want to accommodate the travel demand during the peak hours. How to account for the peak hours? Usually only the hourly volume can cover it. Okay, and here, out of so many different design, so many hourly volumes within 1 year, we are more interested about the design hourly volume. How to determine the design hourly volume? It's the 30th highest hourly volume of the design year. Okay, if you go to the additional notes for this class, so let's say we collect the hourly volume for the entire year. Okay, we sort those hourly volume in the descending order from the highest to the smallest. First question to you is, do you know how many hourly volumes do we have during 1 year? And then for each day we have 24 days, right? 24 hours. And then for 1 year, usually we have 365 days. So overall we have these hourly volumes. So out of them, the 30th highest represents the design hourly volume. Design hourly volume. Why it's not the highest? Why it's not the highest one as the design hourly volume? Because the highest hourly volume just occurs for once for the entire year. It's not economic. And why not use the 50th percentile, the median value? Again, if you use the median value as a design hourly volume, and then half of the year will be under congested. Okay, so that's not convenient for the drivers either. So that's why we use the 30th highest. If you don't know the 30th highest, you can convert the DHV from the AADT by using the K value. The K value usually equals to 0.1 to 0.5, okay, to 0.15, my bad. So that's the range of the K value. Usually the problem statement will tell you the K value directly. Again, the K value is used to convert the daily hourly volume to your hourly design hourly volume. Okay, so once you are done with your design hourly volume, then you might say, okay, I'm done with our design. No, in some situations you have to consider the directional design hourly volume. Why? Why directional design outlet volume? Because if you think about some freeways traffic volume in the morning, so let's use 210 or 10 as example. You can see the westbound direction, the traffic volume is much larger than the eastbound. Why? Because the two directions, they have unbalanced design of the outlet volume. Okay, so this unbalanced volume lead to the unbalanced required number of lanes for each directions. In the morning, usually, let's say if both directions are balanced, you just need to have 4 lanes for each direction. But since in the morning, the westbound direction is much larger than the eastbound, then in the morning probably you need to have 5 or 6 lanes, all right, to accommodate the volume. But in the afternoon, then those vehicles will come back home, will go back home. In that case, they might need 5 or 6 lanes in the eastbound direction as well. So in addition to the design out volume, we also need to consider the directional factor. Okay, so how to calculate the directional factors? Again, let's go to the additional note for the class. For this one, I have 2 directional volume as example. For this southbound direction, let's assume I have 300 vehicles per hour, and this one I have 200 vehicles per hour. Now, how to calculate the directional factor? Directional factor is the dominant directional factor divided by the total traffic volume, okay, in both directions. So in other words, is the larger one is 300 divided by the total is 500. Then the directional factor can be calculated as 0.6, and then in the different license exams, sometimes we found they can also be expressed as 60%, and sometimes they can also expressed as split as 60 and 40. So don't consider as, oh, that means the directional factor equals to 3/2. No, that's wrong. Okay, so never use this numbers. It just simply represents, okay, the directional is split by 40 and 60. In your calculation, you just use the 60 divided by total divided by 60 plus 40, so which is 0.6. Okay, so don't get confused in your future license exam. All right, so now those are the 4 outlet volume. In addition, okay, so if you look at this slide, you can see the largest volume time unit is per day, and then the smallest is hourly. Okay, so how about the time interval less than 1 hour? So in that case, we have to bring the rate of flow into your attention. The rate of flow is the calculated number of vehicles based on the intervals less than 1 hour, usually 15 minutes. Okay, so why, you might wonder, okay, if we have the outlet volume, why we need to consider the rate of flow based on the time interval less than 1 hour? Because we have to consider the variability or peaking that may occur within 1 hour, especially for what? Especially for those signal design. Because signal design, if you give me a 1 hour volume, that doesn't have our design that much. So we prefer those smaller time intervals, usually 15 minutes. Okay, since there is a fluctuation between each 15 minutes, so each 15 minute has its own rate of flow, and the peak 15 minute volume is called V15, and the peak rate of flow is calculated as 4 times V15, and the hourly volume is just simply the total measured number of vehicles during the interval of 1 hour. Let's see one example before we do the calculation together. So now let's go to the special nodes. So let's see, within 1 hour, I divided into 4 different 15-time intervals, the first, second, the third, and fourth. Let's assume for the first 15 minutes we have 200 vehicles, the second we have 300 vehicles, the third we have 250 vehicles, and the last we have 200 vehicles. So you can see the rate of flow for each 15 minutes is what? Is 4 times the 15 minutes. Okay, that is the first 15 minutes, the rate of flow is 800, because rate of flow is calculated number of vehicles based on intervals less than 1 hour. Okay, it's estimated hourly volume. So 15 minutes you have 200 vehicles. Of course, the rate of flow, the estimated hourly volume is 800. Again, the rate of flow for the second 15 minutes is what? Is 1200. And the third 15 minutes rate of flow is 1000. And the last one is 800. Again, you can understand, okay, each peak flow, each 15 minutes has its own rate of flow. The peak rate of flow is 4 times V15. Which one is the peak rate of flow? V15 in our case equals to what? Equals to the second 15-minute interval. So V15 equals to 300, and its rate of flow is 4 times 300. The peak rate of flow is 1200. Okay, that's our calculation. And then the hourly volume, just simply the measured volume during 1 hour. So you just simply plus those numbers, 200 plus 300 plus 250 plus 200, which is 950. Okay, based on the rate of flow, peak rate of flow, and hourly volume, we can calculate the peak hour factor, which is called as PHF. PHF is defined as hourly volume divided by the peak rate of flow. Is the capital V divided by 4 times V15. Guess what does that mean? It means the percent of the hourly volume relative to the largest rate of flow. Okay, so if this number is always less than 1, you agree the PHF is always less than 1, because it's equals to the V divided by V times V15 right here. V15 is the largest 15 minutes, and V is the largest, and the volume is just the sum of all the V15s. Okay, so both numbers are positive value. That's why they are greater than 0 and should be less than or equals to 1. In which situation the PHF will be equals to 1? In which situation? The answer is what? When each of the V15, they are equals to each other. In that case, the PHF will be equals to 1. So the larger the PHF, the more stable of the traffic volume, the less variability within 1 hour, right? And the smaller the PHF, the less stable of the traffic volume within 1 hour. So urban and rural, which one is more stable? Of course, the urban will be more stable. So that's why usually the default value for urban PHF is 0.92, and for the urban is 0.88. So by understanding that, let's get back to our example right here. So for this example, the volume is 950, the peak rate of flow is 1200. So we find the PHF is 0.79. It's relatively small. That means the traffic volume is not stable. All right. So it's even less than the rural traffic statement. Okay, so let's see another example. Let's assume for the first 15 minutes, the number of vehicles is 400. And then the rate of flow will be equals to what? 400 times 4. So equals to 1600. 1600 right here. And then the second rate of flow will be 4 times 500. 4 times 500, which is 2000. The third one is 4 times 700. All right. So 2800. The third one will be 4 times 600. Okay, so that is 2400. So the total volume actually is 2200. The PHF will be equals to, based on our discussion, will be the volume. All right, 2200 divided by 24 divided by the peak rate of flow, which is this one, 2800. So that is our peak rate of flow. All right, so we are done with the peak rate of flow. Now, based on traffic volume, let's see how to calculate the time headway. The time headway is defined as the time between the arrival of successive vehicles at the special roadway point. So in other words, if we have two vehicles, okay, what is the vehicles between the difference of the time, arrival time between these two vehicles when they pass the same roadway point A at these roadway sections? Okay, and what is the arrival time difference between vehicle 2 and 3, and so on, when they pass the same roadway point on the roadway sections? So traffic volume is based on the total number of vehicles per unit of time, usually it's per hour. And then the time headway is used to consider the behavior of individual vehicles in the traffic stream rather than the average traffic stream characteristics. If you know the headway between each vehicles, all right, the travel headway between each vehicles, and then finally you can calculate their average headway among all those vehicles. Okay, we calculate their average time interval. So how to calculate the average? The calculation is very simple. It's the reciprocal of volume. Reciprocal of volume. Why? Let's go to the additional note. So let's assume you have 1800 vehicles per hour. In other words, the 1800 vehicles share the 1 hour. Share the 1 hour. In other words, each two vehicles will be on average they will share what? 2 seconds. Why? Because 1800 vehicles you share 3600 seconds. So the average time headway is the 3600 divided by 1800 vehicles, which is equals 2 seconds per vehicles. That's the time headway. So once you know the time headway, you shall know the volume. Or if you know the volume, you shall know the time headway. So they are in reverse relationship to each other. Alright, so now we are done with the traffic volume and traffic speed. Let's go to the traffic density. The traffic density actually is defined as average number of vehicles occupying a unit length of roadway at a given instant. So let's see, if I have one lane roadways, okay, so from this point to this point, let's assume they are 1 mile, okay, they are 1 mile. And then let me see how many vehicles in between. So the total number of vehicles in between per mile, we call it density. Okay. And what is the relationship between volume, density, and the speed? Okay, their relationship can be expressed by using this equation. The density equals to volume divided by the speed. As we discussed before, the speed usually is the space mean average speed. Okay, so based on their units, you can also know of the density. The vehicle per mile equals to vehicles per hour divided by what? Divided by miles per hour. Okay, vehicle per hour divided by miles per hour will be equals to vehicles per mile. Okay, so from the units, you can also deduct this correlation right here. And for volume, we have different volume measuring devices, and for speed, we have different speed measuring devices. But for the density, it's very hard to measure because you have to have a very large devices and very high level. For example, the helicopter, and then you take a photo, all right, covering 1 mile, and then you count the number of vehicles in between. So it's relative to hard to measure the density. But however, we can use this relationship to calculate their density. You can use this relationship to calculate their density. Okay. So that's why we don't need the density measuring devices. So based on the definition of the density, let's see how can we calculate the distance between successive vehicles. For example, what is their successive vehicle distance in between? The distance in between. Okay, so in this case, we need to use this relationship. We use the number of feet divided by the density. Okay, we can calculate the average space headway. Okay, again, we can see these examples. If, let's assume, within this 1 mile, we have 100 vehicles in between. 100 vehicles, all right? So their density is 100 vehicles per mile. And then what's the distance between two vehicles? The average space headway, it's, in other words, 100 vehicles, they share the 5280. So that's why the average space headway equals to 52.8 feet per vehicles. So up to this point, you know the relationship between density and volume and speed. Okay, and for the volume and time headway, time headway equals to 3600 divided by volume. Okay, you also understand the relationship between space headway and the density equals to 5280 divided by the density. So we have 5 different traffic volume in our case, 5 different parameters: HS, the D, and the V, and S, and time headway. So this is another 3 to 5. As long as you know three knowns, you can calculate all the 5 parameters. That is another popular 3 to 5 set in transportation field. Okay, the first 3 to 5 is what? Is the time, distance, and acceleration, and V initial speed and V final speed. Okay, as we learned from last class. So now let's move on to the next slides. Okay, again, this slide clearly demonstrates our relationship, okay, between speed, volume, and density. Let's focus on the relationship between speed and density. When they have the free speed, when the speed is relatively high, the density is relatively low. Okay, so when the speed is relatively high, the density is relatively low. Let's assume they are as low as 0. So we have this point. Okay, this relatively high speed usually we call it free flow speed. All right, and the second point is the medium speed and the medium density. So that's the second point. Okay, the medium speed and the medium density. And third point is low speed and high density. That's the low speed. Let's assume the speed is as low as 0. Okay, and the density as high as jammed density. So we get these points. So we can connect these 3 points as the straight line. And the first part is a solid line. It represents unsaturated situations. The vehicles can move forward relatively fast. And the second part is the dashed line. It represents the saturated situations. That means the density and volume is relatively high. Okay, and the speed is relatively low. All right, that's the relationship between speed and density. Now let's find the relationship between speed and volume. So for the free speed and the low volume. So free speed and low volume. So this point, right? The speed is relatively high, but the volume is very low as 0. And medium speed and high volume. So medium speed, okay, and high volume. And the third one represents the low speed and low volume. So that is this point, low speed, let's say as low as 0, and low volume as low as 0. So you have these 3 points. If you connect them together, you have this one, and you have the dotted line right here. This one represents unsaturated, and this one represents saturated. Okay. So similar, you can develop the relationship between density and volume, low density and low volume, which is this point, and medium density and high volume, okay, which is this point, and high density and low volume, okay, which is this point. Again, you connect them, you find, okay, this part represents the saturated and this part represents unsaturated. Okay, basically we assume they are symmetrical. So the medium speed usually can be considered as half of the speed, free speed, and medium density we can consider as half as the jammed density, and the maximum volume is the product of medium speed times medium density, okay, because they correspond to the volume maximum right here. So which is product of the free flow speed and jammed density divided by 4. Okay, so that is the speed and volume and density relationship. And the most important is this 3 to 5 sets. So thank you for your watching and look forward to your homework number 1. Bye.